So in this video, we're finally going to get the signal into the computer. We've talked about how numbers are represented by computers, but now we have to figure out how we actually convert an analog signal, like a voltage, into a number that goes into a computer. This is called analog to digital conversion, and I think the name is pretty obvious. We'll go through the details of that. It actually goes through two stages. One is to acquire values of the signal at various times. We'll learn that there's something called the sampling theorem, very important result in this business, in which you can sample a signal without error. Amplitude quantization is another story. Now we have to convert those continuous amplitude values, characteristic of analog signals, into a set of discrete values. That incurs error, as we'll see, and we'll learn how to analyze and control those errors. All right, so let's go over the definition again of an analog and a digital signal. Analog signals are functions of a continuous variable like time, and I show a typical analog signal here. Wiggles around, has a continuous range of values for the amplitude, and these functions of continuous time. Digital signals are discrete valued functions of the integers. So I show as a bubble plot values of a signal here. They're isolated, they only occur at the integers. And you'll notice these various fixed set of amplitudes, and those are the only amplitudes that are allowed because it's a discrete valued function. It's going to turn out that this is that signal gone through an A to D converter, and you may wonder, well, that doesn't look anything like it. How in the world can you go back from the digital signal to the analog one? I'm going to show you can't, but it's a very interesting story when you get into all the details. All right, well, first thing we're going to do is acquire individual values of the signal. And we can describe that in the following very simple way. We're going to start with our analog signal. There it is. And here is our old friend, the periodic pulse train. So the separation between the pulses is T sub s. S means sampling, and T sub s is going to be the sampling interval. The width of each pulse is very narrow. Delta is going to be very small for us. Well, if you just multiply those two signals together, the analog signal times the periodic pulses, you get this waveform shown in the bottom here. And we're going to make delta so small that all that really results is that we get the value of the signal at the center of the pulse. We're going to assume that these pulses are really, really very narrow. Now the question is going to be for us, can we, from these values, can we connect the dots? Can we connect the dots, filling in what is zero so that it looks like the original signal? And the answer is we're going to be able to do that with no error as long as we play our cards right. Let's see how that works. Well, how do you figure that out? You got to look in the frequency domain. That's why one of the reasons we went through all this effort to learn about signals in both time and frequency. So what is its Fourier transform? So what I'm going to do is I'm going to express the periodic pulse sequence in its Fourier series, and we know that that formula corresponds to the coefficient values. So let's do that multiplication by substituting in the Fourier series, rearrange things a little bit so that I put all the functions that depend on time together. The question is going to be, what is the Fourier transform of that? Because once I know that, because the Fourier transform is linear, I know it's just going to be a weighted linear combination of those individual spectra. Well, this is an old Fourier property. You multiply by a complex exponential in the time domain. That corresponds to a shift in frequency, a delay in frequency in the frequency domain. So we get the really simple result from our Fourier properties that we're going to have, each term has a Fourier transform which corresponds to the original signal spectrum, capital S, shifted over by k over Ts, because that is the frequency of that complex exponential. And they're going to get all added up. So it's pretty easy, actually, to find the Fourier transform of our signal, our sampled signal. It's just a weighted linear combination of shifted spectra. Well, let's look at that in more detail and plot it. So I'm going to use for my example the rooftop spectrum, which I like to use. This is known as band limited. It's a very important consideration for sampling. And what that means, its spectrum is 0 beyond some frequency. Here that frequency is W. It also turns out that W is its bandwidth. That's the amount of the positive frequency axis where the spectrum is non-zero. But what's important for us is what the cutoff limit is for the band-limited part of the signal. So that's what the individual spectra look like. Now, when I delay and add them up with constants, this might be what I get. So you can see I have taken the original one, k equals 0. Here's the original spectrum, multiplied by C0. I then shifted over by 1 over Ts, multiplied by C1. I get that one, shifted over by 2 over Ts, and I handle the negative indices the same way. So this goes on forever and ever and ever, as you might imagine. Now, the question is going to be, can I get back the original spectrum? Can I go from this and somehow get back that without error? And the problem is going to be these overlap regions. This is called aliasing. It's a technical term. And what happens in here is that we get these two pieces are added together. They overlap with each other and they're going to add up. That's what this formula says. And once they're added, I can't tell you what the individual components are. If two numbers add up to 3.2, I can't tell you which two unique numbers were added together to get 3.2. It's impossible. So once you get into this area of overlap, I can't tell you what the original signal spectrum was in that region. And here I can, but not in there. I'm in big trouble. So what is the criterion by which you don't overlap? The separation between these is 1 over Ts, and that separation has to be greater than the amount that comes from the part at the origin plus the amount that comes over from that direction. Well, each of those amounts is W, so that has to be greater than 2W. And I can write that the other way by turning this upside down, that T sub S has to be less than 1 over 2W. If we meet this criterion, these individual rooftop spectra will not overlap. And at least we have a chance of getting back to the original signal spectrum. Well, in this case, what I did is explicitly draw it so that the spectra did overlap. And that's what I get for a spectrum here. I get these overlapping areas. Aliasing has occurred because I didn't sample quick enough. TS needs to be smaller. Well, here's what happens when you do let TS be smaller. And now the individual pieces, the individual parts do not overlap. I can see them all very clearly, and that's because I've obeyed the little rule that I derived. Now, can I go from this back to this? How would I do that? And I think the answer is fairly obvious. What I would do is filter. I would apply what's called ideal low-pass filter, having a cutoff frequency of W that would cut out all these higher shifted versions of the spectrum, and sure enough, I get back my original spectrum, multiplied by C0. C0 is just a gain, and I could easily compensate for that little bit What's much more important is to get rid of these frequency overlaps. We do not want aliasing. So, now the criterion for the sampling theorem, which I'm going to point out here, here's the criterion. So we have to have two things. One is the signal has to be band limited, and we're going to assume it's W hertz, and the sampling, the pulse sequence, has to have a period, a sampling interval, that's less than 1 over 2W. And what we have shown, just by example, is that if you obey those two rules, then you get a picture that looks like this. By simply applying a low-pass filter, I can get back the original signal. So if I take my signal values, that's all I have is just the values. Every so often, every TS, if I multiply that times my original pulse sequence, so I take every pulse amplitude and make it S of NTS accordingly, and then pass that through a low-pass filter. That low-pass filter is this filter. I get back the original signal with no error. That is really very nice. And by the way, remember, this is a frequency domain way of looking at it. If it wasn't in the frequency domain, we wouldn't be able to say one way or the other. Now, this criterion is usually not specified in terms of the sampling interval. Rather, it's usually specified in terms of what we call the sampling rate. So the rate, of course, is just 1 over the interval. And so our criterion for obeying the sampling theorem is that the sampling rate has to be twice the highest frequency in the signal S. So this low-pass filter here, by the way, is here to make sure that the signal is band limited. There are some A to D cards out there for computers that are pretty sloppy, and they don't have this first low-pass filter. And so it is possible that you could send in a signal and that would be aliased once you sampled it. But high-quality A to D converters, analog to digital converters, have this front-end filter, which is called an anti-aliasing filter for obvious reasons. It prevents aliasing. Then the sampling rate inside has to be greater than twice the bandwidth of that front-end filter. And if you do that, I can, from these sampled values of the signal, get back the original waveform in continuous time. I have to emphasize that. Just from a few values, I can get back the original signal. Very, very nice. Well, that's the first phase. We have a discrete time signal. Discrete time means we're in discrete time. We only have the signal values every t sub s seconds. But it's not digital yet because the values coming out of here are continuous in general. If you put in a sine wave, we get all kinds of different values. It's not a discrete set of amplitude values. We have to do that phase next, and that's the next part of a real-world A to D converter. So here is the sampling part of the A to D converter, and of course we can get back the original signal without error if we just stop there. But now we have to convert it to a set of discrete values, and that's called amplitude quantization. And I denote the amplitude quantization function by Q, and what it looks like is what's called a staircase function. So this is a function, so any value here in that range gets called a 5, as you can see, and that's how we convert from a continuous set of values into a set of discrete ones. Here I'm going from something that goes from -1 to 1, from something that has integer values 0 to 7. Well, I think you can see this may be a function going this way, but coming back, if I tell you it's 5, I can't tell you precisely what the original signal value was. And that's the error that's inherent in amplitude quantization. Amplitude quantization introduces error. So here's the the signal at various stages in our A to D converter. Here's our original signal. Here it is after it's being sampled, and if the signal was band limited, then I can, from my little discrete values in time, get back the original signal, which I show as this ghostly dotted line underneath. I can connect the dots in exactly the right way. But then once I go through the amplitude quantization part, bets are off. Now I only have 8 possible values for the amplitude, corresponding to the integer 0 to 7, and you can see the layering. And since these values do not correspond exactly to the values over here, there is an error. I cannot get back the original signal. So we better get some understanding of how big these errors can be. That's going to be important. So, and can we control those errors? So here's my quantization function. And let's blow up one of those intervals. Let's look at it in some detail. So every value in this interval is called a 4. Right? So here's my original signal value, and since it's in this interval, it's called 4. Well, once I get a value of 4, how do I translate that back into some amplitude value? There's going to be an error, which I call epsilon, but the question is, what do I use for the value to call it? And I think it makes a lot of sense that the value you want to assign to the amplitude is the value in the center of the interval. If you picked over here, there's a huge error involved. If you picked over here, well, the error may be smaller for this signal value, but one over here is going to incur a large one. And it seems to me a good compromise is just to pick the middle, and you can show that that is the right one to pick. Well, the question is, how big is that error sort of on average? And what I'm going to calculate is the RMS value of the error. So, same calculation we've done before. We take the squared error. We're going to integrate it over the width of the interval. Since we're assuming we're in the center, we go from to plus delta over 2 down to minus delta over 2 relative to that center, and divide by the total width, take the square root, do the integral, and divide by delta. You'll get delta squared over 12. It's a classic answer. So the RMS is the square root of delta squared over 12. Now, a little important fact is, what's delta? Now, I've assumed that the signal is amplitude limited, which is not a bad assumption for most real-world signals. It goes between -1 and 1. Well, in general, the signal goes between plus and minus its maximum magnitude. I think that's pretty obvious. So the total range across here is 2 times the maximum value. The number of quantization intervals is 2 to the b. So I show here 8 quantization intervals. That's what I've used in this example. What is b? It corresponds to 8 quantization intervals. Well, I'm sure that you know, since you know your powers of 2, that 8 is 2 to the 3, so this is what is known as a 3-bit converter. Turns out you can't buy a 3-bit converter. That's way too few. I'm just using it here as an example so we can see what's going on. All right. What I need to do, though, is have some measure of quality of the amplitude quantized signal. And the typical thing that we use is called signal-to-noise ratio. So it's defined to be the ratio of the signal power to the noise power, and noise is quoted here because it's the amplitude quantization error. So the bigger the SNR, the better, the happier I am. That means relative to the signal, the error is small. So what we have is signal plus error, and this is the original signal value. And so the bigger this is relative to that, relative to the error, the bigger the SNR, and I get happy. So let's go through the calculation. So what's the power in the signal? Well, I'm going to assume that for this calculation that my signal is a sinusoid whose amplitude is A. And we know from what we've already done that the power in a sinusoid is the amplitude squared over 2. Epsilon is determined by delta. The power in the error is delta squared over 12. And now delta is going to be twice the amplitude of our sine wave, 2a divided by 2b. And so you simply do that calculation, stick it in, and notice that the amplitudes cancel. So our result is going to apply no matter how big the signal was or how small, as long as the A to D converter takes into account that range of variation, the SNR is fixed. Doesn't matter. And what you get is a somewhat weird answer that's 3/2 times 2 to the 2b. Now, the important part here is the SNR increases exponentially with D. So the more bits you use, the finer the quantization interval, the smaller it is, and the SNR goes up exponentially. So the way to reduce quantization error is to have more bits. It turns out more bits could be a very expensive A to D converter to buy, but no matter how many bits you can use in your A to D converter, there's still going to be some error. We cannot get back the original signal exactly, but the error can be reduced by controlling the number of bits. Now it turns out SNR is not usually stated this way. It's stated in a quantity called decibels. There's a complete video on decibels that you may want to look at if you don't know about the decibel scale. It's a logarithmic scale, and since this is a power ratio, x in dB, it's always written lowercase d, uppercase b, is equal to 10 log 10 of x divided by some reference number. That's how you convert from a number x that you may calculate and express it in dB. Well, the reference here is 1, and after I take the log and take care of it, this is what I get for the SNR expressed in decibels. This term, I think is pretty clear, comes from the 3/2, and I'm going to let you figure out that 6b amounts to 2 to the 2b expressed in decibels. You want to figure that out for yourself. So, what's very common is to have a 8-bit converter. Most computers have at least 8-bit converters, and that means the signal-noise ratio is 48 plus a little bit. Well, 48 is almost 50, and because of the definition of decibels, that's almost 5 orders of magnitude. So with an 8-bit converter, you're almost guaranteed that the signal in general has a power that's 10 to the 5th times the power of the quantization error. And you may say, wow, that really is pretty good. I don't think I need to get much better than that. It turns out there are people out there who think they claim to be able to hear a noise that's that small. That's where the SNR is 50 dB. They claim they can hear that, and I think that's pretty close to the threshold of hearing. So 8 bits may suffice for some applications. For high quality audio, more bits are used. In fact, I want you to go and look up what the CD sampling rate is and how many bits are used in CDs, for the original CDs. I think you'll be pretty surprised at what the answer is. And furthermore, once you know what the sampling rate is, I want you to tell me what the upper limit for the signal is assumed to be. What's the band-limited quantity W for the signal for a given sampling rate used for CDs? Okay, so This is the story of analog to digital conversion. The sampling part, which we see here, occurs with no error. No error at all. It's only the amplitude quantization part that introduces error. It's inherent. We cannot avoid quantization error. But we can have figured out how big it is, and we can control it by using more bits. More bits we use, the smaller the error.